Hi guys! In this video I want to talk about excess reactant. In a previous video I went over limiting reactant and theoretical yield as well as percent yield, but I didn't mention what we do with the excess, which is something that we would want to know because I'm going to have to take it into account when I run a real reaction. So as a reminder, the limiting reactant is the one that gets completely used up and ends up stopping the reaction. It's also the one that limits the amount of product we can make, which is why it's called the limiting reactant. But because the limiting gets completely used up, it means that I'm going to have leftover excess reactant at the end. And to find out how much of that excess is left, you have to do 3 steps. So the first is you still need to calculate the theoretical yield because that is going to allow you to determine what the limiting reactant is. And once you know what the limiting reactant is, then you can convert that limiting reactant into the excess reactant because that is going to tell us how much of that excess was used up in the reaction. And once I know how much was used, I can take that used amount and subtract it from the amount of excess that I started with, and that will tell us how much is left. So let's look at an example. So I have a reaction here. Copper 1 oxide reacts with oxygen gas to form copper 2 oxide. So I'm going to need to write my formulas. So I need the charges first. So copper 1, this 1 for the transition metal, copper, tells me that this particular copper has a +1 charge, and oxygen is a -2 charge. So then if I absolute value those and then cross and drop, I get the formula for copper 1 oxide is Cu2O. So copper 1 oxide reacts with oxygen gas, and oxygen is one of the diatomics. So oxygen gas is written as O2. So copper 1 oxide reacts with oxygen gas to form copper 2 oxide. So this copper has a +2 charge. Oxygen still has a -2. So when I absolute value cross and drop, I get the formula for copper 2 oxide to be CuO because those 2's end up canceling out. Now I need to balance this. So I see on this side of the equation I end up having an odd number of oxygens, and that's not going to work. So I want to turn that odd number, that 3 total oxygens, into an even number. So I'm going to put a coefficient 2 here, which means now I have 2 oxygens plus 2 oxygens. That gives me 4. And I also now have 4 coppers. So that makes it easy. I can put the coefficient 4 here. So now I have 4 coppers, 4 oxygens. 2 plus 2 oxygens gives me 4, plus my 4 coppers, and now it's balanced. So now that it's balanced, I can look at my problem. If 4.18 grams of copper 1 oxide reacts with 5.77 grams oxygen gas, what is the theoretical yield of copper 2 oxide? So I know that this is a theoretical yield problem or a limiting reactant problem because I'm asked specifically for the theoretical yield of copper 2 oxide, and I'm also given an amount of both reactants. So I'm going to have to do 2 stoichiometric conversions. The first with the copper 1 oxide into copper 2 oxide, and then the second with the oxygen gas into the copper 2 oxide. So I'll start with my copper 1 oxide. So I have 4.18 grams of copper 1 oxide. This is the copper 1 oxide, so Cu2O. And the first rule of stoich is get to moles. So grams Cu2O on the bottom, moles Cu2O on the top. And that will factor out or cancel my grams. Now I want to convert substances. I want out of copper 2 out of copper 1 oxide and into copper 2 oxide. So moles Cu2O on the bottom to factor out, and moles of CuO, my copper 2 oxide, on the top. So that cancels moles of Cu2O. Because I was given a unit in grams, I probably want to end in grams as well, so I'll go ahead and do that. Factor out the moles and end up in grams. So then moles to grams, this is a molar mass conversion factor. So 1 mole would be the molar mass of Cu2O, which I have already calculated out from my periodic table to be 143.099 grams of copper 1 oxide for every 1 mole of copper 1 oxide. A mole-to-mole conversion factor uses the coefficients from a balanced equation. So 4 moles copper 2 oxide for every 2 moles copper 1 oxide. Then I have another grams to moles, so it's molar mass again. For every 1 mole of copper 2 oxide, it is the molar mass, which I have found to be 79.549 grams. So now I'm ready to calculate 4.18 times 1 times 4 times 79.549 along the top, and 143.099 times 2 times 1 along the bottom. So 4.18 times 4 times 79.549 along the top is that value, divided by 143.099 times 2 along the bottom gives me this, and I need 3 sig figs, so 4.65 grams of copper 2 oxide could be made from my copper 1 oxide. So now I need to convert my grams of oxygen gas to copper 2 oxide. So 5.77 grams of O2. Get to moles first, so grams of O2 on the bottom, moles of O2 on the top. That will cancel out the grams. Then I'll switch substances, so moles of O2 on the bottom to moles of copper 2 oxide along the top, and then moles of O2 will cancel. And then I'll take it into grams because I took this into grams, and I need to end up with the same unit and the same substance to compare them. So moles CuO on the bottom, grams of CuO on the top. So grams to moles, that's molar mass. For every 1 mole of O2, it is 31.998 grams of O2. Mole to mole, that's a mole ratio. For every 4 moles of copper 2 oxide, I have 1 mole of O2. And then grams to moles is again molar mass. For every 1 mole of copper 2 oxide, it is 79.549 grams of copper 2 oxide. So then I'm ready to do 5.77 times 1 times 4 times 79.549 along the top, and then just 31.998 along the bottom. So 5.77 times 4 times 79.549 is that along the top, and then divided by 31.998 from the bottom, with 3 sig figs is 57.4 grams of copper 2 oxide. So then I'm going to compare 4.65 grams of copper 2 oxide to 57.4 grams. So this is clearly the smaller answer. So this 4.65 grams of copper 2 oxide would be my theoretical yield. And then the reactant that produced it was the copper 1 oxide. So the copper 1 oxide is my limiting reactant. I need to know this so that I can answer the second part. How much excess is left over? So if my copper 1 oxide is my limiting reactant, that automatically makes my oxygen my excess reactant. So I'm going to take my amount of limiting reactant and convert it into grams of my excess reactant, O2. So I'm going to start with my 4.18 grams of copper 1 oxide. And I'm going to go to moles first. So grams copper 1 oxide into moles copper 1 oxide. And then I'll change my moles of copper 1 oxide into moles of my oxygen gas, because that's my excess. And then finally I will take my moles of oxygen gas and go into grams of oxygen gas. So 1 mole is the molar mass of copper 1 oxide, 143.099 grams. Mole ratio, for every 2 moles of copper 1 oxide, I have 1 mole of O2. And then molar mass here for grams, so 1 mole of O2 is 31.998 grams of O2. So now I'm ready to calculate. 4.18 times 31.998 along the top divided by 143.099 times 2 along the bottom. And I need 3 sig figs still, so 0.467 grams of O2. Now this tells me that in using up all of my copper 2 oxide, my limiting reactant, I only had to use 0.467 grams of O2. So this is my amount of O2 that was used in the reaction. So to find how much was left over, I take how much oxygen gas I started with, 5.77 grams, and I subtract what was used, 0.467 grams, and that will tell me how much I have left. So 5.77 minus 0.467 gives me 5.303 grams of O2 mathematically. And then for sig figs, this is subtraction, so I'm only going to look at decimal places. So 2 decimal places is the smallest, so that would round to 5.30 grams of O2 is left. So at the end of this reaction, I'm still going to have 5.30 grams of O2 left over. Now to finish it out, if the actual amount of copper 2 oxide produced was 4.28 grams, what is the percent yield? So percent yield is the actual amount, so 4.28 grams copper 2 oxide divided by the theoretical yield, which was 4.65 grams copper 2 oxide. And I'm going to take that and I'm going to multiply it by 100 to find my percent yield. So 4.28 divided by 4.65 times 100 is 92.0% yield. Not bad, because anything above 90 is what we're looking for.